5.5 is the substitution rule. This is the last section we're going to be doing. Let me change this. This is 5.5. But the substitution rule is a way that we can do integrals that aren't polynomials. The ones we did in the last section were all polynomials, x squared plus 2x plus 1, and they're separated by plus and minus signs. So it's not too bad to do those integrals because you can break them up there. But sometimes the integral doesn't work out that way. And so if you have an integral that can't be written as polynomials, this allows you to create a substitution that makes the integral a polynomial. And usually when they do this, they use the letter u, but that's just by custom. They call it u substitution a lot of times. And the expression that you should be substituting for u is usually found in parentheses, in exponents, or in the argument of a trig or log function. So you can either write the integral as a polynomial or a simplified trig or log function. Or exponential function. Those are when they're in the powers. And what you have to do is you have to replace the function and the dx, because you're changing the letter for dx. So in the problem set, there's stuff called variations on the substitution method. You don't have to do those variations. All I'm worried about is that you can do problems in my new book at 17 through 32 and 39 through 52. That's just a regular substitution method without having to do this weird change of variables. So don't worry about variations on the substitution method. The examples are very similar to what might show up on a test. So this first one is 2x times x squared minus 1 to the 99th. What I could do is I could expand this all out and it would be a polynomial. I could do x squared minus 1 times x squared 99 times, which is painful to do. So instead of doing all that, I can do a u substitution instead. And a lot of times you find what you want to make u in parentheses. So in this case, I'm going to make u the stuff in parentheses, x squared minus 1. So as I rewrite this integral, it allows me to rewrite that stuff in the parentheses as u. But there's something else you have to look at, and it's this dx. Dx tells me that the letter that's in the integral is the letter x. But I'm not using the letter x anymore. Now I want to use the letter u. So I can change that. I can make dx show up by taking the derivative. The derivative of u with respect to x, the derivative of x squared is 2x. The derivative of 1 is 0. And I'm going to solve this for dx. Then I can replace the dx in my formula. So I get du is 2x dx, and du over 2x is dx. So I can replace my dx with du over 2x. And that's another reason that I knew the x squared minus 1 was my u, because the derivative of that, 2x, will help me cancel the other stuff. If you'll notice, the 2x here and the 2x here cancel, and this becomes the integral u to the 99th du. Well, this says the letter u is in my integral, and that's what's there, the letter u. So I can just find the integral without any problems. Now we can use the power rule. I add 1 to that, and I divide by that number, and I put in a plus c because there's no bounds on this integral. But my original function didn't have u's in it. Instead of u, my original function had x squared minus 1. So I'm going to replace my u with x squared minus 1 because I only needed the u to come up with the integral. Once I found the integral, I can put my x's back in. So this is the idea of u substitution. You figure out what you want to make u, and you write it down. And that lets you replace something with a u. And then you take the derivative of your u and solve it for dx. And that lets you replace the dx as well. And you'll be able to cancel something and end up with an integral that you can do. Let's look at another. Here's an exponential one. X e to the x squared. Usually if you have to make a u, it's in parentheses or in powers. Here, x squared is in the power. But notice the derivative of x squared is 2x. It'll allow me to cancel that x there when I replace the dx. So I can start to rewrite this integral. This is the integral of x e to the, well, I'm not writing x squared anymore. Now instead of x squared, I write u. The derivative of u with respect to x is 2x. So I'm going to solve this for dx, and I get du over 2x. is dx. So I can replace the dx with du over 2x. And notice the x's cancel. Now that 2 on the bottom is a 1/2 when I factor it out. And I just have 1/2 integral e to the u du. Well, the integral of e to the u is e to the u, so this is 1/2 e to the u plus c. That constant of integration is there because there's no bounds. But I'm all done integrating because the integral sign went away. So now I can put my u back in. Instead of u, I can write x squared. 1/2 e to the x squared plus c. So there's an example where the u is in the power. And there's another one. Here's an example where u is in the square root. In this case, I have a 4x cubed in the bottom and an x squared on top, but I need to do a u substitution because it's not a polynomial. So I let u be 1 minus 4x cubed, and I take the derivative so I can replace my dx. The derivative with respect to x is negative 12x squared. So I solve this thing for dx. Du over negative 12x squared equals dx. So when I rewrite this integral becomes 2x squared divided by the square root of u du over negative 12x squared. And if you'll notice, the x squareds cancel. 2 goes into 2 once, and into negative 12 6 times. So I can factor out that negative 6 on the bottom. It becomes a negative 1/6 because it's on the bottom. And that's a square root of u, so it's u to the 1/2. But I need to move that to the top before I can use the power rule, so I write that as u to the negative 1/2. But now all my letters are u, and I have a du in there, so I can integrate with the power rule. Add 1 to negative 1/2, you get positive 1/2. But dividing by positive 1/2 is like multiplying by 2. And so I can simplify this. And I get negative 1/3 u to the 1/2 plus c. But I'm all done integrating. That's the reason I did the u, was to integrate. So now that I'm done, I can replace my u with 1 minus 4x cubed. But everything else is the same. And that's the answer to the original integral. If I take the derivative of this, I get back the stuff that was in the integral to begin with. Replace your u, replace your dx, and you'll be able to come up with an integral that you can simplify more easily. The last couple examples are going to be some integrals that have bounds in them. It's the exact same idea in how to solve them, although how you deal with the bounds is up to you. So example, I have an x squared plus 1 in the bottom in parentheses and an x on top. To work this integral, I'm going to want u to be the x squared plus 1 in the bottom. I take the derivative. Du over dx is 2x. So du over 2x is dx. So I can rewrite this integral. I have a 2x on top. I have u squared on the bottom. And instead of dx, I got du over 2x. Notice the 2x's cancel. And so this becomes the integral of 1 over u squared du. I have to bring that to the top, and that's u to the negative 2 du. And now I get to choose what I want to do with my bounds. The problem is 0 and 2 go with x. They don't go with the u's I just put in. They go with the x's I just put in. So I can integrate u to the negative 2. I add 1 to the power. I get u to the negative 1 over negative 1 from x equals 0 to x equals 2. U to the negative 1 is 1 over u, and the negative 1 on the bottom makes 1 over u negative. But I can't plug in 0 and 2 because those go with x's. So before I can plug in my 0 and 2, I have to put my x's back in, and that means I can replace u with x squared plus 1. Now I can put in my 0 and my 2. So I put in 2, and I put in 0, and I look and see what I get when I integrate. I get negative 1 over 5 plus 1, which is 4/5. This is 5 on the bottom, so negative 1/5. Those two negatives make a positive 1. There's another way I could have approached it. Right here, when I changed to use, I could also have changed bounds, and that's another way to do this. It's called changing bounds. You don't have to change bounds. You can do it the way I did it above. That's fine. If you put your x's back in, you can use the original bounds to come up with it. But to change the bounds, I could have used my u. The original bounds for x were from 0 to 2. But I said in the beginning that u should be x squared plus 1. So if I wanted to use bounds for u, I would have to go 2 squared plus 1. The 2 would become a 5. And 0 squared plus 1, that would become a 1. If I can type it in right. And so if I'd have done that with the bounds, then this would have been, oh, this is 1. Then the integral right there that was in the box would have been the integral from 1 to 5 of u to the negative 2 du. And still that's u to the negative 1 over negative 1. But now I can just plug in 1 and 5 for u. I don't have to put my x's back in. So this is negative 1 over u from 1 to 5, which is negative 1 over 5 minus negative 1 over 1, which is 1/5, negative 1/5 plus 1, which is 4/5. So when you do these problems, it's up to you how you do them. You can either put your x's back in which case you can plug in your original bounds, or when you substitute your u's, you could have changed the bounds for x into bounds for u by using the substitution. And then you don't have to put your x's back in. You can just plug those bounds into u. I usually change the bounds, because then I don't have to keep track of what letter I'm using. I'll just change the bounds to work it. So let me try one more of these where we have to work the bounds. Now I'm going to change the bounds on this one the whole way. In this case, I'm going to let u be the stuff under the square root. 9 plus p squared. Notice the derivative of p squared is 2p. It'll let me cancel out the p on top. I take the derivative, du over dp is 2p, so du over 2p is dp. Now I'm going to change my bounds, so I don't have to put my x's back in. My original bounds for x, 4 was the big one, 0 was the small one, but u is 9, oh I'm sorry, that's for p, because these bounds went for the original p. To figure out my u bounds, I plug 4 in to 9 plus p squared, and I get 25. I plug 0 into 9 plus p squared, and I get 9. So this new integral is going to have bounds that go from 9 to 25. These bounds will match the u that I'm going to put in. P over the square root of, the stuff under the square root is what I'm calling u. And instead of dp, I write du over 2p. We notice that the p's will cancel. That 2 on the bottom is a fractional 1/2, 9 to 25. And u is, the square root of u is u to the 1/2. I'm going to bring that to the top as u to the negative 1/2. But now I can just integrate. I don't have to put the x's back in because these bounds are made for the letter u. So the integral of u to the negative 1/2, I add 1. I get u to the positive 1/2 divided by 1/2 from 9 to 25. I don't need to put any x's in. Well, dividing by 1/2 is like multiplying by 2. And notice these 2's will cancel. And so this is just u to the 1/2 from 9 to 25. And so I plug in 25 minus 9. And this gives me 5 minus 3, which is 2. So the area under that integral is 2. So notice when I'm working through these, I decide what to make u, I replace my dx or dp, and I change my bounds if they're there. And that allows me to create an integral that I can easily integrate.